Hey everyone! Welcome back to the final part of our leaf disease detection project using deep learning. This project helps identify diseases in plants by analyzing leaf images. It's useful for farmers, researchers, and anyone interested in smart agriculture. If you haven't watched Part 1 and Part 2 yet, make sure to check those first. The links are in the description and pinned comment below. Before we jump into training and evaluation, let's do a quick recap of what we've done so far. Part 1. Data preparation. Explored and visualized sample images of leaf diseases. Organized images into training and validation folders. Checked class distribution to ensure the dataset was balanced and ready. Part 2. Model building. Built a custom efficient NetB4 model with pre-trained ImageNet weights. Added dense layers with batch normalization and dropout for better performance. Compiled the model using Atom Optimizer and sparse categorical cross-entropy. Model is ready to accept images and classify them into multiple leaf disease categories. Today in Part 3, here's what we'll do. Train the efficient NetB4 model on our dataset. Visualize the training history, accuracy, and loss curves. Evaluate the model on validation test data. Predict and evaluate with confusion matrix. Summarize the project from start to finish. Let's move on the coding section. Train the efficient NetB4 model. In this step, we train the efficient NetB4 model using the pre-processed training and testing data. The model is trained for 10 epochs with a batch size of 64, and validation data is used to monitor its performance after each epoch. During training, the model learns to recognize different leaf disease patterns by adjusting its internal weights through backpropagation. A training log appears showing epoch-wise accuracy and loss for both training and validation sets, indicating how the model improves its learning and performance across epochs. Visualize model performance, accuracy, and loss curves. In this part, we define a function called plot history to visualize how our model performs during training. It plots two graphs, one for accuracy and one for loss, showing both training and validation results over all epochs. By calling plot history, we can clearly see whether the model is improving, overfitting, or underfitting. These curves help us evaluate how well efficient NetB4 learned to classify the leaf diseases. Two smooth line charts appear side by side. The left graph shows training versus validation accuracy improving with epochs. The right graph shows loss decreasing, ideally for both training and validation sets. Evaluate model performance, training versus validation metrics. In this step, we evaluate our trained efficient NetB4 model on both training and testing datasets using the evaluate function. It returns the loss and accuracy values, which help us measure how well the model performs on known and unseen data. If the training accuracy is much higher than the validation accuracy, it indicates overfitting. But if both accuracies are close, it means the model has learned to generalize properly. The result shows the validation accuracy, validation loss, train accuracy, and train loss. These metrics help us understand whether the model performs consistently across both datasets. Higher accuracy with lower loss indicates good model performance. Final model evaluation on test data. In this final step, we evaluate the efficient NetB4 model on the test dataset to measure its real-world performance. The evaluate function returns both loss and accuracy values. We then print the test accuracy as a percentage to easily interpret how well the model performs on unseen data. The printed accuracy shows the model's final performance on the test dataset. A higher percentage means better classification ability. saving the trained efficient NetB4 model. After training and evaluating the model, we save it using the save function, so it can be reused later without retraining. The model is stored in Google Drive at the specified path in .h5 format, which preserves both architecture and learned weights. The file efficient NetB4 model.h5 is successfully saved in the given directory. It can now be loaded anytime for prediction or fine-tuning without running the full training process again. Plot efficient NetB for confusion matrix. This code defines a function to plot a confusion matrix for the efficient NetB4 model. It first predicts the classes of the test set, then compares them with the true labels to create the confusion matrix. Using Seaborn's heat map, it visualizes correct and incorrect predictions for each class, helping us understand which classes the model predicts well and which it confuses. A heat map is displayed showing the predicted versus actual classes for all categories. Darker diagonal cells indicate correct predictions, while off-diagonal cells show misclassifications, providing a clear view of model performance per class. Efficient NetB4 classification report. This code predicts the classes of the test dataset using efficient NetB4 and generates a classification report. The report shows precision, recall, F1 score, and support for each leaf disease category, helping us evaluate how accurately the model classifies each class individually. A table is displayed with metrics for every class. Precision: how many predicted positives were correct? Recall: how many actual positives were correctly identified? F1 score: balance between precision and recall. Support: number of samples per class. This provides a detailed assessment of the model's performance across all categories. Load custom VGG19 model with fixed dropout. This code installs Keras applications and defines a custom dropout layer called fixed dropout to handle noise shapes correctly during model loading. Using custom object scope, we safely load the previously saved modified VGG19 model from Google Drive, ensuring that the custom dropout layer is recognized. The modified VGG19 model is successfully loaded into memory as loaded model and is ready for predictions or further evaluation. Predict and visualize a single leaf image. This section loads a single image from the validation set, resizes it to match the model's input, and scales pixel values to. The image is then passed to the loaded VGG19 model to predict its class. The predicted class is determined by taking the argmax of the model's output. Finally, the image is displayed with matplotlib, and the predicted class is shown as the title. The image of the leaf is displayed with a title showing the predicted class, e.g., predicted apple healthy, providing a visual. Predict and display a raspberry leaf image. This code loads a single raspberry leaf image from the validation dataset, resizes it to the model's expected input size, and normalizes the pixel values. The image is then passed to the loaded VGG19 model for prediction. The predicted class is extracted using argmax and displayed as the title of the image with matplotlib. The image is shown on the screen with the predicted class label, for example, predicted raspberry healthy, allowing quick visual verification of the model's prediction. Predict and display a pepper leaf image. This code loads a single pepper leaf image affected by bacterial spot from the validation dataset, resizes it to the model's required input dimensions, and normalizes its pixel values. The processed image is then fed into the loaded VGG19 model for prediction. The predicted class is determined using argmax and displayed as the title of the image with matplotlib. The leaf image is displayed along with the predicted class label, e.g., predicted pepper bell bacterial spot, allowing us to visually confirm the model's classification. Let's quickly recap what we've done so far in our leaf disease detection full project. Part 1. Data preparation. Installed libraries, mounted drive, loaded dataset, processed and labeled images, visualized samples, checked class distribution. In Part 2, model building. Built VGG16, VGG19, and efficient NetB4 with pre-trained weights. Added dense layers, batch normalization, dropout. Compiled models for leaf disease classification. And Part 3, training and evaluation. Trained efficient NetB4, plotted accuracy loss curves. Evaluated performance with test data, confusion matrix, classification report. Made predictions on new leaf images. Real-time detection ready. Now that we've seen all the steps, from preparing the data, building the models, to training and evaluating, let's take a look at the overall outcome of the project. Full workflow from data model prediction. Ready-to-use leaf disease classifier. Notebook and dataset available for hands-on practice. So that's it. We've successfully completed the full leaf disease detection project using deep learning. You'll find the complete notebook and dataset links in the description, so make sure to check that out. In the next project, we'll explore another exciting real-world AI application, so stay tuned. If you found this tutorial helpful, don't forget to hit the like button, subscribe for more AI project tutorials, and share this with your friends.